All right, we have an 800 kilogram smart car driving over a hill. And so this is the situation. There's the car. Woohoo! All right, we want to determine the centripetal acceleration of the car as it goes over the hill. So this part's straightforward. A is v squared over r. That'll be 20 squared divided by 20. And then we simplify this out. We'll end up getting 20 meters per second squared. Now the net force acting on the car, that's going to be F net. It's going to be m times a, which will be 800 times 20. And when we simplify this out, this is going to be 16,000 newtons of force. All right. Now, we're going to go ahead. We've got a speed of 20 meters per second at the top. And here's what this says. It says treat downward as the positive direction and upward as the negative. So let's draw a free body diagram. We have a normal force pushing up on the car. We have the weight of the car pushing downwards. And using this advice right here, the way we set up our equation to get the normal force is we use the free body diagram to tell us that the weight force pulling down fights the normal force pushing up, and the effect is that the car has this centripetal acceleration, MAC. Now we actually calculated in the previous problem that the 16,000 newtons, so let's go ahead and solve for the normal force. So we're going to end up getting 8,000 minus Fn equals 16,000. Now we get a very interesting answer here. When we isolate the normal force, we're going to end up getting negative 8,000 newtons. And I just want to address something here for a second. The number here is correct. It turns out in real life, this number is actually an impossible number. And I'm going to show you why in part D. So this is the correct number. This is what you should write down. This is absolutely the right calculation. It just turns out I gave you an impossible problem without realizing it. It's kind of like, it's like that Hannah Montana song that Molly alerted me to. Nobody's perfect. I've got to work it. Sigh. Okay, so part D. The maximum speed the car can go before losing contact with the ground. So the idea here is we're at the top of this hill and we're at the maximum speed. We're about to lose contact. Well, if we're losing contact with the ground, that implies the normal force is 0. So when we set up our equation, we'll still write Fg minus Fn equals, now this is an unknown speed, that's mv squared divided by r. So we have Fg equals mv squared divided by r. Let's put in our numbers. We'll actually put in here 800 times 10. Just to be clear, this Fg here is mg, which is 800 times 10. That's where I'm getting that from. Equals 800 times v squared divided by 20. Now, when we work all this out, we're going to get 8,000 equals 40v squared. So we're going to end up getting 200 equals v squared. So when we isolate v by taking both sides, v ends up being 14 meters per second. So here's the idea. The maximum speed we can actually go at is 14, and then we lose contact with the ground. It's impossible to go any faster up the hill. If you try, you're actually just going to launch into the air. So it turns out this 20 meters per second I got here, that's a nice number to do a calculation with, but it turns out it's impossible. Now, all of these numbers are correct. These are the numbers you should get for this practice test, and nothing's wrong with it. But it's just a little technicality I wanted to point out here that if you notice, my maximum speed is smaller than the speed I gave you, which means I actually gave you an impossible problem. So that's page 2 of the exam. We'll move on to page 3 in the next video. I know you can hardly wait.